In this lecture, we shall learn that how we can calculate the we can say Cshp, that is aerodynamic shape factor for solar panel mounted on the roof structure. Now, when we're talking about the solar panel mounted on the roof, we are talking about either this example. So in here, you can see that how the solar panels have been mounted on the rooftop of a building, and or this kind of example. So the difference we can say between this example and this example is that in this case, the pitch, that is the slope of the roofing, that is very, we can say, steep, and alpha is, we can say, very high. In this case, alpha is a little bit lesser also, and there is this we can say a small surface also that is given on the bottom, so that wind can easily pass. Now the difference here, as per my practical experience, is that I always prefer to not to give the space between this rooftop and, we can say, solar panel. Now that is my point of view again, because when wind shall blows from the bottom also, it shall result in suction. And the solar panel manufacturers also, the one that I have worked with, they're also of opinion that it is better to fix the solar panels on the roof itself. So obviously they are water resistant. It's not like that rain shall harm them, but the only thing that is harmful for them is the wind. And if we do ensure that wind shall strike on the face, and after the face it shall put pressure on the, we can say, the roofing arrangement, which is again supported with the strong structural elements of the, either with the truss or either with the beams. So that shall result in effective transfer. But if we create a secondary structure here on the again on the top, and fix them with the help of anchors, and saying that wind shall also flow from the bottom, so that may result in the, we can say, somewhat disturbance also. It may be a case where there shall be a local deflection, or the sheeting can also get damaged. I repeat, that is my point of view. So let me just come to the picture here. So in here, the, we can say, as per the, this is the snapshot taken from AS1170. So this is the panel mounted parallel to the roof plane, and in here basically there are these two angles, that is theta is equal to 0 and theta equal to 90, and this is the alpha and this is the S. So S is basically given as 50 to 300 mm. Now if I am an engineer, I need to design that. I won't be going forward for the 300 mm gap. I shall be looking forward for 50 mm gap, and that 50 mm gap can also be, we can say, sealed also from both ends, so that wind does not get into inside the bottom, and shall have some secondary effect onto the structure. So that is my point of view. After that, when we're talking about the code, so figure B.9, panel mounted parallel to the roof plane, the whole area, let us suppose the span, or we can say the longitudinal length of the roof, that is D. So that is divided into three part here. So when we're talking about theta is equal to 90 degrees, and this is the upwind end, this is the upwind, we can say, central and downwind end. So when we're talking about theta is equal to 90, this is the upwind end, this is the central portion, and this is the downwind end. And when we're talking about theta is equal to 0, so let me just draw that in the other perspective. So let us say this is the structure on which we need to install our solar panels. In this case, theta is equal to 0 shall be this angle. So we can say theta is equal to 0, and on top of these, we can say, top of these the solar panels are installed. So in this case, basically, it shall be, we can say, striking onto this particular direction. So theta is equal to 0 in this case. So when we're talking about theta is equal to 0, this is the upwind end portion. This is the, we can say, upwind central. And this is the, we can say, upwind end and upwind central. Yeah. So these are the two portions. And after that, when we're talking about the other side, that is on the back side here, if we draw a view from here, so let us say this is the back side of this particular roofing structure. So this is the downwind end, and this is the downwind central. So these two are the, we can say, upwind end portion, and these two are the upwind, we can say, central, sorry, these two are the downwind end portion, and these two are this is the downwind central portion. So let us say we downwind central has been denoted as the, we can say, orange color, and downwind end has been denoted as the, sorry, downwind end has been denoted as the green color. So this is basically the green color here. After that, when we're talking about the upwind portion, let us say upwind end portion, this is this portion here, and again upwind end should be this portion here, and upwind central, it shall be, we can say, this portion here. Let us just color it as black only. So this is the upwind central portion. So these are the zonification when we're talking about theta is equal to 0 degree. So when wind is striking from this particular direction, this is theta is equal to 0. This is also theta is equal to 0 degree. So according to that, we can just simply find out the values as per the, we can say, alpha. And obviously it can be interpolated also. So let us suppose if it is between 5 to 10 degrees. So if the alpha is 7.5 degrees, then we simply need to refer to this particular table. Assuming that in our case alpha is equal to 7.5 degree, so we can just simply find out the coefficient. So for upwind end portion, the positive coefficient is 0.8, the negative coefficient is minus 1.1. So upwind end, we can just simply write down here, that is minus 1.1 and plus 0.8. The same shall be here also, minus 1.1 and plus 0.8. And after that, when we're talking about the upwind central portion, this is basically minus 0.8 and plus 0.5. Minus 0.8 and plus 0.5. Similarly, when we're talking about the downwind end and downwind central portion, this is basically minus 1.1 and 0.5. Minus 1.1 and plus 0.5. And at the same time, the other value shall be downward central, minus 0.8 and plus 0.4. Minus 0.8 and plus 0.4. So these are the values when we're talking about theta is equal to 0 degree, and when we're talking about alpha equal to 7.5. So we can just simply refer to these values here. And at the same time, when we're talking about theta is equal to 90, so these are the values when we're talking about theta is equal to 90. So it is not that we do need to do much more, we can say, zonification as per the the wind engineering studies that has been done. For alpha between 5 to 30 degree, for theta equal to 90, the values are same only. So there's no as such different values when we're talking about 5 to 30 degree and when wind is blowing perpendicular to the roofing arrangement. So let me just draw the roof again. So let us just say that when wind is striking from this particular direction, in here the wind was striking from theta is equal to 0. Right now we are talking about theta is equal to, theta is equal to 90 degree. So in here basically the first portion that is getting strike to this, that is basically, we can say, yeah. So that is basically, we can say, our yeah. So that is basically the, we can say, upwind end portion. So these two are, we can say, upwind end portion, and the central portion that can be left as black itself. So this is the upwind end. This is, we can say, a downwind end portion, and middle one is the central portion. So upwind end and downwind end, these are the coefficient, minus 1.7 and minus 1.1, plus 0.4 and plus 0.5. So obviously the coefficient are higher when we are talking about this area, and the coefficient are lower when we're talking about this area. So on the basis of that, we can just simply find out the values. So in our case, we just need to restrict our discussion onto these coefficient. So these are the coefficient, we can just simply refer to the different areas, and on the basis of that, we do need to ensure that the we can say the main structure that is designed correctly as per the coefficient that was given. So maximum to maximum, the coefficient is going as high as minus 1.7. So positive Cshp correspond to the net downward pressure. So when the pressure is Cshp is positive, it means that the wind is striking it down. And when it is a negative, that is in this case when wind is flowing from this particular direction, we can see that for upwind end portion, it has experienced suction as high as minus 1.7 times. So that shall get critical when we're talking about theta is equal to 90, and at the suction value that is quite high when we're talking about this particular case. So I hope the picture is now clear to you, that you are clear about the we can say direction also. You're clear that it is not that the dimension of the solar panel, dimension of the roof matter. The only thing that matter is the we can say the alpha, that is the inclination of the roofing. But at the same time, we do need to ensure that the these coefficient are basically net pressure coefficient only. So sorry, these are coefficient are basically aerodynamic shape factor itself, that is Cshp. So we can just simply consider that in our analysis, that is Cshp can be simply referred to these values, and according to that we can design our structure.